University and laureate of 2007 Turing Award. The academic community you are joining today is dedicated to excellence in research and teaching, despite the hostile environment that politicians used to create for Greek universities. And in this environment, as researchers and teachers, we are passed to the very edge of silence. However, dedication to science and permanent effort constitute our response to obstacles and challenges. If the Greek governments do apparently not recognize our effort, the international academic community eloquently recognizes the results of it. The University of Crete is ranked 48th in the annual Time Higher Education 100 under 50 ranking of the world's elite universities under the age of 50, announced a few days ago. This is an improvement compared with our previous ranking and reflects well on the academic community in Crete in the face of worsening recession conditions, which impact severely higher education institutions and other public organizations in Greece. In addition, according to the 2014 Leiden University Classification for Research, the University of Crete in the field of natural science is ranked 5th in Europe and 43rd in the world above Imperial College. Since its foundation, our university established strict criteria for conferring the title of Doctor Honoris Causa. We recognize the outstanding achievements and contributions of individuals at the international level in physical and social science, medicine, literature, and arts. We also recognize academics, scientists, researchers, humanists, and scholars who have made a significant pioneering or revolutionary contribution to their area. In the past, we have conferred honorary degrees to Jorge Luis Borges, the poet, Jean-Marie Len, the laureate of Nobel in chemistry, François Jacob, the laureate of biology, to cite some of them. Today, as rector of the University of Crete, I am honored to confer to you, Professor Edmund Clarke, the degree of Doctor Honoris Causa of the University of Crete, with the title, honor, and privileges that are proper to it. Dear Edmund Clarke, dear colleague, we are happy and proud that you share with us, by accepting this honor, our combat for academic and scientific excellence in this challenging era for Greece.
Προσφώνησε από τον κοσμήτωρα της Σχολής Θετικών και Τεχνολογικών Επιστημών του Πανεπιστημίου Κρήτης, καθηγητή Μιχαήλ Καρουδάκη.
Κύριε πρόσωπε του Δημάρχου Ηρακλείου, κύριε Πρίτανη, αγαπητοί συνάδελφοι, αγαπητοί φοιτητές, καλημέρα σας και ευχαριστούμε που ήρθατε σε αυτή την τελετή αναγόρευσης του καθηγητή Clarke σε επίτιμο διδάκτορα του Τμήματος Επιστήμης Υπολογιστών της σχολής μας. I will speak in English, and for me it's a great honor and pleasure to welcome Professor Edmund Clarke in the School of Science and Engineering of the University of Crete as a honorary doctor. Professor Clarke is well known worldwide for his extremely innovative research in the area of model checking and the formal verification of hardware and software correctness. He's combining his optimal mathematical background. For those of you who don't know, he initially studied mathematics. He received the bachelor's from the University of Virginia and the Master of Science also in the area of mathematics from Duke University before getting his PhD from Cornell. And so he combines this very good mathematical background with his intuition and deep knowledge in computer science to develop algorithms for the check of protocols used in heavy industrial applications of computer systems. These algorithms are rigorously supported by theorems proving their effectiveness and correctness. The area is extremely important for both today and future science, and the methods developed by Professor Clarke and his team will continue to be applied to even larger systems in which absolute correctness is essential. Professor Clarke is a winner of a great number of distinguished awards, including the Turing Award, which was presented to him in 2007, together with Alan Emerson and Joseph Sifakis for their role in developing model checking into a highly effective verification technology that is widely adopted in the hardware and software industries. Professor Nicolaou will explain more about Professor Clarke's work, and Professor Clarke himself will present it during his talk later on, which has been considered as the distinguished lecture of our school. From my side, I would like to express my enthusiasm that a distinguished professor and researcher joins our family in the School of Sciences and Engineering, and I congratulate the Department of Computer Science for their suggestion to include Professor Clarke in the group of honorary doctors. I'm sure that today will mark the continuation of long research collaboration between the group of Professor Clarke and the group of professors and scientists of the Department of Computer Science, the contribution of whom in bringing our school at the top of the ranking of School of Sciences in Europe, as our rector explained before, is essential. Carnegie Mellon today means University of Crete. So, Professor Clarke, welcome again to our family.
Προσφώνηση από τον πρόεδρο του Τμήματος Επιστήμης Υπολογιστών του Πανεπιστημίου Κρήτης, καθηγητή Παναγιώτη Τσακαλίδη.
Αξιότιμε κύριε Πρίτανη, κύριε Κοσμήτορα, κυρίες και κύριοι συνάδελφοι, αγαπητοί φοιτητές. It is with a great honor that after 30 years of history, the Department of Computer Science of the University of Crete confers its very first honorary doctorate degree on Professor Edmund Clarke, Systems University Professor of Computer Science and of Electrical and Computer Engineering at Carnegie Mellon University. Professor Clarke is a pioneer in the field of model checking. His role in creating an automated methodology for finding design errors in computer hardware and software was recognized by ACM with a 2007 Turing Award, the most prestigious award in computing. Back in the early 80s, about the time that Professor Clarke started educating his first doctoral students at Harvard University, among them a good colleague of ours, on the other side of the globe, a brand new department of computer science, the first of its kind in Greece, was inaugurated here in the island of Crete. That department was founded by people with a very specific vision: to make the place known internationally for high-quality research in all areas of modern computer science, as well as for the high level of commitment to educating and building career opportunities on behalf of its students. 30 years ago, the original founders had the vision, but even more importantly, they had the ability to turn their dream into something very real and concrete. A place in Greece as close as possible to the good American and European computer science and electrical engineering departments. Thanks to the vision and know-how of its founders, who understood the need to cut through the restraints of public bureaucracy, the innovative and youthful spirit of the University of Crete, and a fortuitous state of affairs, the department started with a clean slate, attracting high-caliber Greek scientists from abroad to fill early faculty positions. Today, more than ever, that original aspiration remains the same. This place has always been extrovert. It always invited new people, it blended the new with the established, it has been constantly renewed and retooled. That continuous effort did place Crete on the technology map of Europe. We're very proud that our faculty is recognized internationally. Among us, there are 2 members of Academia Europaea and 2 recent European Research Council prestigious grant recipients. Most of the faculty are research active, with sustained publications, research funding, and student production. The faculty is characterized by an opportunity-seeking mentality that parallels that of high-quality schools in Europe and North America.
and it is not me who's saying that. This is an excerpt from the latest external evaluation report on the department. So, after 30 years of effort, the people who care about this department are quite confident about the quality and the results of the work performed here. We are also quite confident that we can finally confer an honorary doctorate on a pioneer in computer science, and that this person actually will show up to receive it. So yes, it is a great honor that we have Professor Clarke here with us today. A great honor, but also a great pleasure that comes with the thought that despite the harsh times, this place has come of age. Thank you.
Προσκαλησία από τον κύριο Γεώργιο Βλαχάκη, εκ μέρους του Δημάρχου Ηρακλείου.
Αξιότιμο κύριε Πρίτανη του Πανεπιστημίου Κρήτης, κύριε Στεφάνου, αξιότιμο κύριε Κοσμήτρο της Σχολής Θετικών και Τεχνολογικών Επιστημών, κύριε Ταρουδάκη, αξιότιμο κύριε Πρόεδρε του Τμήματος Επιστήμης Υπολογιστών, κύριε Τσακαλίδη, ελογιμότατοι κυρίες και κύριοι αγαπητοί φοιτητές, ο Δήμαρχος Ηρακλείου, λόγω ανηλυμένων υποχρεώσεων, αδυνατεί να παραστεί στη σημερινή εκδήλωση προς τιμή του καθηγητή Clarke. Ωστόσο, χαιρετίζει την πρωτοβουλία αυτή του Τμήματος Επιστήμης Υπολογιστών, όπως άλλωστε και κάθε μελλοντική πρωτοβουλία του Πανεπιστημίου Κρήτης, η οποία όχι μόνο προάγει την επιστήμη, αλλά ιδιαίτερα όταν τιμά, επενεί και συγχαίρει τους ανθρώπους οι οποίοι συμβάλλουν στην πρόοδο του ανθρώπινου πολιτισμού. Κύριε καθηγητά, κύριε Clarke, καλώς ήρθατε στην Κρήτη. Η παρουσία σας αποτελεί ιδιαίτερη τιμή όχι μόνο για το Πανεπιστήμιο Κρήτης, του οποίου είστε προσκεκλημένος, αλλά και για το Ηράκλειο ολόκληρο. Ευχόμαστε και ελπίζουμε η παρουσία σας εδώ να είναι μια παρουσία συνεργασίας και σε μια επόμενη παρουσία να είναι μια παρουσία συνεργασίας με το Δήμο Ηρακλείου. Σας ευχαριστώ.
Παρουσίαση του έργου του τιμόμενου από τον καθηγητή του Τμήματος Επιστήμης Υπολογιστών του Πανεπιστημίου Κρήτης, κύριο Χριστό Νικολάου.
Κύριε Πρίτανη, κύριε Κοσμήτορα, κύριε Πρόεδρε, κύριε εκπρόσωπε του Δημάρχου Ηρακλείου, κύριοι συνάδελφοι, αγαπητοί φοιτητές, καλησπέρα σε όλους τους φίλους και όλες τις φίλες που μας κάνουν την τιμή να είναι μαζί μας σήμερα σε μια ξεχωριστή και ιστορική στιγμή για το τμήμα μας, όπως άλλωστε είπε και ο Πρόεδρος, το Τμήμα Επιστήμης Υπολογιστών του Πανεπιστημίου Κρήτης, μιας και αναγορεύει τον πρώτο επίτιμο διδάκτορα στην ιστορία του. Θα πω μερικά λόγια ακόμα στα ελληνικά, αλλά μετά για χάρη του τιμωμένου θα συνεχίσω στα αγγλικά. Και σας ευχαριστώ για την κατανόησή σας. Ο Edmund M. Clarke ξεκίνησε ως μαθηματικός. Τον κέρδισε όμως η πληροφορική. Εργάστηκε ως ερευνητής με τεράστια συνεισφορά στο πολύ δύσκολο πρόβλημα της επαλήθευσης της ορθότητας προγραμμάτων που εκτελούν ζωτικές λειτουργίες όπως ο έλεγχος ενός αεροπλάνου ή ενός διαστημόπλοιου εν πτήση. Για τη συνεισφορά του αυτή τιμήθηκε το 2007 με το βραβείο Turing, που θεωρείται το βραβείο Νόμπελ της πληροφορικής, αλλά και με πλήθος άλλων βραβείων. Το βραβείο Turing το μοιράστηκε με τον Allen Emerson και με τον Ηρακλειώτη συμπατριώτη μας, Σύφη Φάιτ. Είναι καθηγητής στο Πανεπιστήμιο Carnegie Mellon, τον ΗΠΑ, και να σας πω τώρα και ένα μυστικό, εντός εισαγωγικών. Ο Ed Clarke έχει ήδη ιδιαίτερες σχέσεις με το Πανεπιστήμιο Κρήτης, που όπως ξέρουμε είναι το κατεξοχήν ερευνητικό πανεπιστήμιο στην Ελλάδα, μια και ο Mellon υπήρξε ένας από τους παλιούς του πρώτους φοιτητές. Και μάλιστα υπήρξα και συμφοιτητής του Allen Emerson, ο οποίος είναι ο δεύτερος στο βραβείο Turing του 2007. Ας μου επιτρέψετε λοιπόν τώρα να γυρίσω στα αγγλικά. Edmund M. Clarke is the Four Systems University Professor of Computer Science at Carnegie Mellon University. He initially studied mathematics, receiving a BA from the University of Virginia in 1967 and an MA from Duke University in 1968. He received his PhD from Cornell University and taught at Duke and Harvard universities before joining CMU in 1982. He has received numerous awards for his contributions to formal verification of hardware and software correctness, including the IEEE Good Award, the ACM Kanellakis Award, the ACM Turing Award, and the Kate Herbrand Award. Dr. Clarke is a member of the National Academy of Engineering and the American Academy of Arts and Sciences. Most recently, he received the 2014 Franklin Institute Bauer Award and Prize for Achievement in Science for Verification of Computer Systems. Ed's career has focused on mathematical reasoning about computer systems, with an emphasis on reasoning about the reliability of those systems. Reasoning about reliability is necessary but very hard. A computer system executes simple operations, but those operations can occur in a staggering number of different orders. And why is that, you may ask? Well, the reason is that the computer system may have to respond to several external events coming from the world surrounding the computer system. Some of these events may happen simultaneously, and moreover, their succession in time cannot be predicted, cannot be assured. Examples of these events are users entering data through keyboards or screens, sensors sending temperature or radiation readings that have to be acted upon, messages arriving through the network, etc. This makes it extremely hard for the designer to envision every possible sequence of event succession and predict its consequences. Yet every one of these sequences, no matter how infrequently executed, must be correct. If a program executes an incorrect sequence, at the very least it will waste the user's time, while at the worst it could cause injury or loss of life. Let me now use Ted Kirkpatrick's words as written in the ACM Turing Award website to describe why this is a very hard problem. The sequences become even more difficult to envision in systems with multiple programs running at the same time. Mathematical reasoning, and specifically the expression in formal logic, in principle, is sufficient to describe every possible sequence and ensure that all of them are correct, even for simultaneously running programs. In practice, however, classical mathematical reasoning is awkwardly matched to describing the many possible execution orderings in a computer system. Early researchers addressed this mismatch by developing logical forms better suited to describing computer systems. One of the first was Tony Hoare. Hoare's logic could be used to prove that every possible execution of a system would only execute an acceptable sequence of operations. This opened the possibility that systems could be proven to perform according to specification every time, no matter the circumstances. Clarke's early research strengthened the foundations of Hoare's logic and extended his method. Although Hoare's methods worked for smaller systems, it was close to impossible to apply to systems of any real size. The dream of powerful, effective methods for reasoning about all possible orderings of the system remained unfulfilled. In 1977, Amir Pnoeli introduced temporal logic, an alternative logic for verifying computer systems. As the name implies, temporal logic allows explicit reasoning about time. In temporal logic, it is possible, for example, to express statements of the kind, this condition will remain true until a second condition becomes true, the until operator. Clarke and his student Alan Emerson saw an important possibility in temporal logic. It could be directly checked by machine. Whereas Hoare's logic required the designer to consider every detail of both the system and the argument about the system's correctness, Brunelli's logic could be implemented in a computer program. Clarke and Emerson realized that the program could exhaustively construct every possible sequence of actions a system might perform, and for every action, it could evaluate a property expressed in temporal logic. If the program found the property to be true for every possible action in every possible sequence, this proved the property of the system, for the system. In the language of mathematical logic, Clarke and Emerson's program checked that the possible execution sequences form a model of the specified property. That's why the term model checking appeared. Working independently, Jean-Pierre Kay and Joseph Sifakis developed similar ideas. The technology of model checking was born. A great strength of the model checking approach is that when it detects a problem in a system design, the checker points out an example sequence of actions that gives rise to the problem. The error traces provided by model checking are invaluable for designers because the traces precisely locate the source of the problem. Although the 1981 paper demonstrated that the model checking was possible in principle, its application to practical systems was severely limited. The most pressing limitation was the number of states to search. Early model checkers required explicitly computing every possible configuration of values the program might assume. For example, if a program counts the millimeters of rain at a weather station each day of the week, it will need 7 storage locations. Each location will have to be big enough to hold the largest rain level expected in a single day. If the highest rain level in a day is 1 meter, the simple program will have 10 to the 21st power possible states, slightly less than the number of stars in the observable universe. Early model checkers would have to verify that the required property was true for every one of those states. Systems of practical size manipulate much more data than the simple example above. The number of possible states grows as well at an explosive speed. This rapid growth is called the state space explosion. Although early model checkers demonstrated that the technology was feasible for small systems, it was not ready for wider use. Clarke and his student Ken Macmillan had a fundamental insight. The state space explodes because the number of states a memory location can assume is much, much bigger than the size of the location itself. The memory location is compact because it encodes many potential states, but only contains one at a time. Clarke and Macmillan observed that this process could be applied in reverse. With the right encoding, many potential states could be represented by a single value. From the literature, Macmillan found an encoding that met the twin goals of tersely encoding multiple states, while at the same time permitting efficient computation of formulas in temporal logic. The new representation dramatically reduced the storage required to represent state spaces, in turn reducing the time required to run a model checker on systems of practical size. They call these new systems symbolic model checkers. In 1995, Clarke, Macmillan, and colleagues used this approach to demonstrate flaws in the design of an IEEE standard for interconnecting computer components. Before this, the reliability of such standards had been informally analyzed, leaving many rare cases unconsidered and potential errors undiscovered. This was the first time every possible case of an IEEE standard had been exhaustively checked. With enhancements such as these, model checking has become a mature technology. It is widely used to verify designs for integrated circuits, computer networks and software by companies such as Intel and Microsoft. Model checkers have been used to analyze systems whose state space is 10 to an exponent of 120, which is substantially larger than the number of atoms in the observable universe, which is 10 to the 80th. The fight against state explosion continues, of course, and Ed, I'm sure, will tell us more about it in his lecture. It is hard to do justice to Ed's work in such a short time. His work extends to other systems beyond the computer systems. For example, Ed and his research group have started work on modeling biological systems. Before I finish, however, with this faint attempt to describe the breadth and depth of Ed's research contribution, I would like to talk to you about Ed Clarke as I have known him, as my teacher and my doctoral thesis supervisor. Ed has this unique ability to have a vision on how deeply theoretical results can have groundbreaking application in important practical matters. Model checking is probably the most famous example of his ability. But there are other examples, such as foreseeing the applicability of reconfiguration algorithms for fault-tolerant distributed systems. That was a field that was just starting to be explored in the 80s, and which later exploded into a major area of distributed computing, the area, for example, of self-healing, reconfigurable autonomic distributed systems. Ed encouraged me to look into this set of problems for my thesis, and luckily for me, I listened to him. This area proved to be not only very fruitful from an academic point of view, but also of significant practical importance. IBM took up a variation of this algorithm that we developed with Ed, called it the ICU-CME algorithm, and used it for a new, at that time, generation of multiprocessor shared disk operating system. This is how I landed my first job at IBM Research, as a postdoctoral fellow, before even finishing my PhD thesis. But Ed is not only inspirational for his students, he can also be very patient with them. Such was the case when he asked me to use temporal logic to prove the correctness and reliability of the so-called alternating bit protocol, an algorithm that allows users to transmit, with some level of fault tolerance, messages to each other. After a big effort, I produced a proof that was awkward, extremely long, cumbersome, and hard to follow. More importantly, the proof was wrong. That was deeply embarrassing to me, but Ed graciously helped me to correct it, and I hope that at least I gave him enough motivation to continue with his model checking work. He was right then, and he is right now. Simpler and hopefully automatic proof methods, such as model checking, have to be found for computer systems verification to become practical. So Ed inspires his students and is patient with them. In addition, he cares for them. Together with his wife Martha, they were my adopted family in Boston, where I studied. This was how they made me feel, by being a frequent guest at their family dinner table. I remember during the last period of writing up my PhD thesis, when the pressure was building up to finish, when you could see the light at the end of the tunnel, and yet, when so much remained to be done, Ed would call me every morning at home to ask, "Good morning, Christos. Did you sleep well? Did you have a good breakfast?" When I said, "Yes, okay, now you come to the office. I'm waiting for you." So, this is why it is with the greatest pleasure and feeling very honored that I proudly presented today some aspects of Ed's research work. Ed is a great teacher, my teacher, and a great researcher, a model computer science researcher. Thank you very much.
Ανάγνωση του ψηφίσματος της αναγόρευσης και του διδακτορικού διπλώματος από τον πρόεδρο του Τμήματος Επιστήμης Υπολογιστών, καθηγητή Παναγιώτη Τσακαλίδη.
Με την ομόφωνη απόφαση της συνέλευσης του Τμήματος Επιστήμης Υπολογιστών τη 17η Δεκεμβρίου του έτους 2013 και της κοσμητείας της Σχολής Θετικών και Τεχνολογικών Επιστημών τη 16η Ιανουαρίου του έτους 2014, αναγορεύεται επίτιμος διδάκτορας ο Edmund Clarke, καθηγητής του Πανεπιστημίου Carnegie Mellon, τον ΗΠΑ, για την εξαιρετική συνολική επιστημονική του παρουσία και τη συμβολή, για το ρόλο του στην ανάπτυξη του ελέγχου προτύπων σε μια εξαιρετικά αποτελεσματική τεχνολογία επαλήθευσης που έχει ευρέως υιοθετηθεί από τις βιομηχανίες υλικού και λογισμικού, στην πρόοδο της σύγχρονης επιστήμης υπολογιστών, στην εκπαίδευση της υπολογιστικής προτυποποίησης και ανάλυσης σε πολύπλοκα συστήματα, όπως είναι τα βιολογικά, συμβάλλοντας έτσι στη διεπιστημονικότητα και στην πρόοδο της βιολογίας και της ιατρικής. Το Τμήμα Επιστήμης Υπολογιστών και η Κοσμητεία της Σχολής Θετικών και Τεχνολογικών Επιστημών αποφάσισαν επίσης ομόφωνα να αναγράψουν σε μεμβράνη το παρόν ψήφισμα που θα αναγνώσει ο πρόεδρος του Τμήματος Επιστήμης Υπολογιστών και θα επιδώσει στον τιμόμενο ο κοσμήτορας της Σχολής Θετικών και Τεχνολογικών Επιστημών. Αναγόρευση. Το Τμήμα Επιστήμης Υπολογιστών και η Κοσμητεία της Σχολής Θετικών και Τεχνολογικών Επιστημών έκριναν ομόφωνα τον Edmund Clarke, καθηγητή του Πανεπιστήμιου του Carnegie Mellon, τον ΗΠΑ, άξιο να αναγορευτεί επίτιμος διδάκτορας του Τμήματος Επιστήμης Υπολογιστών της Σχολής Θετικών και Τεχνολογικών Επιστημών του Πανεπιστημίου Κρήτη. Ο κοσμήτορας της Σχολής Θετικών και Τεχνολογικών Επιστημών, Μιχαήλ Ταρουδάκης, καθηγητής του Τμήματος Μαθηματικών και Εφαρμοσμένων Μαθηματικών, αναγορεύει δημόσια τον Edmund Clarke, επίτιμο διδάκτορα του Τμήματος Επιστήμης Υπολογιστών, και του απονέμει όλες τις προνομίες που απορρέουν από το πανεπιστημιακό αυτό αξίωμα, αυτό είναι το διδακτορικό δίπλωμα. Ο κοσμήτορας της Σχολής Θετικών και Τεχνολογικών Επιστημών, Μιχαήλ Ταρουδάκης, καθηγητής του Τμήματος Μαθηματικών και Εφαρμοσμένων Μαθηματικών, ύστερα από ομόφωνη εισήγηση της συνέλευσης του Τμήματος Επιστήμης Υπολογιστών και ομόφωνη απόφαση της Κοσμητείας της Σχολής Θετικών και Τεχνολογικών Επιστημών, απονέμει τον τίτλο του επίτιμου διδάκτορα του Τμήματος Επιστήμης Υπολογιστών της Σχολής Θετικών και Τεχνολογικών Επιστημών του Πανεπιστημίου Κρήτης στον Edmund Clarke,
Επίδοση των μεμβρανών από τον κοσμήτορα της Σχολής Θετικών και Τεχνολογικών Επιστημών, καθηγητή Μιχαήλ Ταρουδάκη. Καλούμε τον πρίτανη να προσέλθει στο βήμα για την επίδοση του μεταλλίου. Επίδοση του μεταλλίου από τον κύριο Πρίτανη, καθηγητή Ευρυπίδη Στεφάνου, στον Edmund Clarke. Ομιλία του τιμόμενου με θέμα Model Checking and the Verification of Computer Systems.
Can everyone hear me? It's a great honor to be here today and to accept this award. Indeed, it is one of the high points of my academic career. It is also very pleasant to see my former student, Christos Nicolaou. He was my second PhD student when I was teaching at Harvard. He wrote a brilliant PhD thesis and has continued to do great things ever since. Model checking is an automatic verification technique. It has been used successfully for hardware and software verification and for verifying things like communication protocols as well. The first person to see the need for verification was Alan Turing. You may have heard of him before. He, in addition to the award, his techniques are still used in computer science quite widely. By the way, he was a marathon runner. I prefer this picture of Turing to the ones that are sometimes used. Model checking is an automatic method for verifying hardware and software designs, or concurrent systems in general. Let's see, I cannot see my slides myself. I'm going to have to put this right on this. It was developed independently by myself and my student, Alan Emerson, when we were at Harvard, and by Joseph Safakis and his student, Kellia, in the early 1980s. The assertions are written as formulas in propositional temporal logic. Temporal logic is a notation for reasoning about the ordering of events in time without introducing time explicitly. You can say that one event must precede another event, or that two events can't happen at the same time. The notation was originally developed by philosophers and linguists for talking about the way that tense is used in natural languages. So it's perhaps a little bit, it's probably not that surprising that it would have, that it would be applicable to reasoning about time in computer systems. The verification procedure in model checking is algorithmic rather than deductive in nature. You don't construct a proof of correctness. You have a program that checks correctness. So model checking has a number of advantages over other approaches to verification. You don't construct proofs. It's fast compared to other rigorous model methods such as automated theorem proving. It produces diagnostic counterexamples when the specification doesn't hold. There's no problem with partial specifications, and the logics can easily express many of the properties that are needed for reasoning about concurrent systems. Now, of these, probably the most important is the counterexample feature. If a program contains an error, then model checking can find a counterexample that will take you almost directly to the source of the error. One of the first examples that we did was the Intel Pentium floating point division error. Some of you may remember this error. In the original Intel Pentium chip, there was an error. You could write arithmetic expressions in certain applications and get what was obviously the wrong answer. The algorithm that Intel used for floating point arithmetic had a lookup table, and that table had 4 missing entries, and that caused the problem. The cost was $400 to $500 million, or that was the estimate of the cost. Soon after the error was made public, a former CMU student who had taken one of my classes and was then working at Intel called me on the phone and said, told me to send him one of my students. I sent him Zhudan Zhao, who was a student of mine at Carnegie Mellon, and he was able to show that model checking could have found the bug in the Pentium chip, and moreover that the corrected chip did indeed have the bug fixed. Now, I'm not the only one who uses model checking to verify complex systems. Gerard Holtzman at NASA's JPL, Jet Propulsion Laboratory, has developed a model checker, the spin model checker, and the Promula language for doing somewhat the same thing. He has applied it to most missions launched in the last decade, including the Curiosity Mars probe, which is still, the last I heard, it was still functioning correctly up on Mars. Now, many hardware companies use and develop model checkers. Intel, IBM, and Microsoft makes intensive use of software model checking. NEC that uses a model checker, Varvel, to analyze code, and they've analyzed about 40.5 million lines of code and found more than 1,000 bugs and bad coding patterns. The main disadvantage of model checking is the curse of dimensionality. The term is due to Richard Bellman, who also came up with the original idea for dynamic programming. He wrote, in view of all that we have said in the foregoing sections, the many obstacles that appear to have been surmounted, what casts the pall over our victory celebration? It is the curse of dimensionality, a malediction that has plagued the scientists from the earliest days. So here are some examples of the curse of dimensionality. A 2-bit counter has 4 states, and an n-bit counter has 2 to the nth states. Now, if you take 2 3-bit processes, and if you take 2 3-state processes, and you find their parallel composition, then you will get a system with 9 states. In general, if you have m processes, each with n states, then you will get a parallel composition with n to the mth power states. Now, the curse of dimensionality is that the system, the size of the system, grows exponentially with its dimensionality. The dimensionality can be the number of variables, or the number of bits, or the number of processes. This makes the system much, much harder to reason about. Fortunately, in most of the cases in the past 30 years that we've been using model checking, we have been able to keep up with the curse of dimensionality by using sophisticated data structures and good engineering. Now, there are two types of temporal logic. Linear temporal logic, which determines patterns on infinite traces. A formula is composed of atomic propositions, Boolean operations, and temporal operators. A proposition, an atomic proposition, will be true of a trace if it holds in the first state of the trace. XA will be true of the trace if A holds at the next state on the trace. FA will be true of the trace if sometime in the future along the trace A holds. GA will be true if A holds globally in the future. And A until B will be true if A holds true until B becomes true. It's also possible to model time to use a branching time, to use branching time models. The state machine at on the left-hand side of the slide if we fix a starting node, say the blue node, then we can unwind the state transition graph to obtain an infinite tree. Now, we don't actually try to do that. Indeed, we couldn't. But we use such trees for giving the semantics of our logic. The logic that we use, or the first logic that we used, was CTL, or computation tree logic. A formula like EFG would be true at the root of the computation tree if there exists a path, that's the E, and sometime in the future on that path there is a state that is true. We say that G will possibly become true. AFG will be true at the root of the computation tree if along every path sometime in the future G will become true. We say that G is inevitable in this case. AG little g will hold at the root of this computation tree because along every path G holds at every state. We say that G is invariant in the previous case. EG little g will be true if G holds along at each state along a path that starts at the root of the tree. Now, CTL uses the four operators that I've just described, plus universal and existential versions of the next time operator, and universal and existential versions of the until operator. CTL star is a more expressive logic that allows more complex nestings. You can interleave path formulas and state formulas in many complicated ways. Now the model checking problem is easy to state. Let M be a state transition graph, and let F be the specification expressed in temporal logic. We want to find all states S of M where the formula F is true. Now, model checking algorithms were given back in the 80s for most temporal logics, and in fact, most of those algorithms had complexity that was linear in the size of the model. But the algorithms were not so useful in practice because of the enormous size of the models that you wanted to check. Even linear complexity wasn't good enough. Now, here is another example that shows how you might use a model checker. And suppose that you want to check you've built a new microwave oven, and the oven has 4 state variables. Start, can't see my own screen. Start, close when you close, which will hold when you close the door of the oven. Heat, and error. Oh, I should look back there. That's much bigger. I'm going to look back there now. Then I can see what I'm supposed to say. So initially, the tilde means false. So in the initial state, all the state variables are false. You can close the door and go to the state in the middle. You can press the start button and go to the state on the bottom. And then the oven will begin to heat up. And the start button will reset to false. And you can circle, you can loop in that state for a considerable amount of time. And so one of 2 things happen. Either a timer goes off and the food remains in the oven with the door closed, or someone tries to open the oven while the food is cooking. In that case, the heat goes off immediately. Now, you can also try to start the oven without first closing the door, and we assume that even if you subsequently close the door, the oven won't heat up. You have to close the door first, and if you get in the state on the lower left, you can push a reset button and perhaps get back on the right path. Now, the property that we would want to check in this case is that the oven doesn't heat up until the door is closed, and we can write that a little bit more formally as not heat up until door closed, and that we can express directly in temporal logic as not heat up until door closed. Now, in model checking, we start with a description of, say, a piece of hardware, and an informal specification of what it should do in English or some other natural language. And then we compile the hardware into a state transition graph, and we usually informally or manually get a formal specification from the informal specification. And then we check algorithmically, and this is perhaps the most important part of my talk. Model checking is algorithmic. It's not deductive in nature. There is a program that checks the correctness of formulas. Now, to give you another little example, suppose that we have this state transition graph, and there is a start node and a stop node, and we want to determine if the bad state with the evil stop sign is unreachable. Well, in this case, that's clearly correct, since all of the transitions are away from the node with the stop sign. But suppose we move the stop sign so that it labels the node shown now. Then the model checker will produce a counterexample, and the counterexample is a path that takes us from the start state to the node to the node that violates that is labeled with the stop sign. Now, I think that Christos, in his introduction, mentioned that in 1992 we verified the IEEE FutureBus Plus cache coherence protocol. We found a number of previously undetected errors in the design of the protocol, and that was the first time that formal verification had ever been used to find errors in an IEEE standard. The development began in 1988, but all previous attempts to validate it were informal, so they failed to catch these errors. Now, there have been, I think, four major breakthroughs in model checking. Symbolic model checking, I think Christos also mentioned this. We had been representing models explicitly using linked list structures in the first model checking systems. And my student, Ken McMillan, the person on the right, was able to show that you could represent the model symbolically using binary decision diagrams and obtain a much more concise representation. Another breakthrough that I really didn't have anything to do with, but I think is very important nonetheless, is the partial order reduction. The partial order reduction says that if two actions are independent, then you can exploit that independence and execute them in either order. You can and get the same result. So you can do A before B or B before A, and you'll get the same result. So when you build the product space, you only have to include one of those interleavings. Now, whoops, I missed one thing here. Let me go back to symbolic model checking. Christos also mentioned this as well. With symbolic model checking, we can handle systems with 10 to the 20th states. We worked a little harder, and we were able to go up to 10 to the 100th states, and we worked a little harder still, and we were able to go up to 10 to the 120th states. Now we know that that's the number of states, but I'm not so sure that number of states alone is a very good measure of complexity. So after this, after we did this, we stopped using this number of states alone as a measure of complexity, but I don't know what a better measure of complexity is. Now, another breakthrough was bounded model checking. This, in bounded model checking, you use fast stat solvers, that might sound like a contradiction in terms of fast stat solver. We all know that SAT is NP complete. But actually, SAT turns out to be, in practice, it turns out to be not such a hard problem. And it can be used to often you declare success when you can reduce a problem to SAT. So what we do in this case is we write down a propositional formula that has the form shown on the slide. I is the initial state predicate, T is a transition relation, and P is the property we want to check. Let's see if let's try to see if there is some error in the first case steps. So the formula says that V0 is the initial state. There's a transition from V0 to V1, a transition from V1 to V2, and so on, Vk minus 1 to Vk, and the property fails at one of those states. Now, if this formula is satisfiable, we assume that the V's are Boolean variables. If this formula is satisfiable, then there's an error in the first K states. That's as mathematical as I'll get today. Armin was able to check an example that a circuit that had 10,000 latches and 10,000 inputs, a really large sequential circuit, and the formula had 4 million variables and 12 million clauses, and the shortest bug was of length 37 was found in just 69 seconds. Now, the next approach that I think is a big breakthrough, Bob Kershan, who is a good friend of mine, wrote a book in the mid-90s that was related to model checking, his view on model checking. And there was a portion of the book that I couldn't understand. So I gave the book to my student, Yuan Liu, and Yuan spent a long time looking at the book, and finally figured out what Kershan was trying to do. And it turned out to be quite an important task. So we, when we understood it, we called it counterexample guided abstraction refinement. And I'll explain that in just a moment. I asked Kershan why he explained this technique in such an obscure manner, and he said that it was the most important idea in the book, and he didn't want to give the reader too much help. So, in order to understand counterexample guided abstraction refinement, we need to talk about what abstraction means in model checking. We start with a state transition graph and an abstraction mapping. The abstraction mapping maps the set of concrete states, the set of states of M, to the set of abstract states of M sub alpha. We group the states into equivalence classes, and we map those equivalence classes to states in M sub alpha. So those of you who know a little bit of mathematics will recognize this as a kind of quotient construction. And we map the states in the red states to the red node, the green states to the green node, and the blue states to the blue node. Now, there'll be a transition from red to green because there's a transition from some red state to some green state. And there'll be a transition from some red state to some blue state because there'll be a transition from red to blue because there's a transition from some red state to some blue state. There'll be a transition from blue to green because there's a transition from some blue state to some green state. And finally, notice that there's a transition from one blue state to another blue state. Because of that transition, we get a self loop on the blue node in the abstract system. Now, this self loop that we get on the blue state will turn out to be important in a moment. Now, we were able to prove the following theorem. If a property holds on the abstract model, then it must hold on the concrete model. So if it holds of the abstraction, it must hold of what you start with. And there's some technical conditions, but I'm not going to go into those. So here is an example that shows why we need that explains why the theorem only goes in one direction. If we have a traffic light, a cycle that can go green, yellow, red, and repeat, then one property we'd like for it to have is that infinitely often red holds. In other words, globally, that's AG, it's always inevitable, that's AF, that red will hold. Red will always repeat. So what we do, suppose we do the following. We put red in an equivalence class by itself and green and yellow into the same equivalence class. And then we map these to an equivalence class that we call red and an equivalence class that we call go. And there'll be a transition from, let's see if I can get it here, there'll be a transition from red to go because there's a transition from red to green. There'll be a transition from go to red because there's a transition from yellow to red. And there'll be a self loop on this state because there's a transition from green to yellow. So we have this this self loop on the go state, and that means that we can have what we call a spurious counterexample. We can get go can repeat over and over and over again, and that of course is not a behavior that we would want of our traffic light. So we'll see this idea come up again, that this is an artifact of the abstraction. Now, what we want to do is develop an automatic abstraction methodology. We want to be able to start with very abstract model and then refine it. And as we refine it, we may get spurious counterexamples. And eventually, however, we hope that we'll either get, we'll either say the system is verified or give us a counterexample. Now, that leads to what we call counterexample guided abstraction refinement, or CGAR. We start with a circular program, we construct an abstract model, we verify the abstract model. When we verify the abstract model, we don't get an error, then we know that there's no bug in the original model, because this is an over-approximation of the original model. Now, if we do get a counterexample, when we check the abstract model, we have to make sure that the counterexample wasn't added when we constructed the abstraction. And what we have to do is simulate the counterexample on the original circuit or program. If the simulation is successful, we found a bug. If the simulation is not successful, then we get a spurious counterexample, and we use that to refine the abstraction. So this brings me to a question that I'm frequently asked, and I want to say a little bit about this before I stop. Is it possible to model check software? According to Wired News on November 10th, 2005, when Bill Gates announced that the technology was under development at the 2002 Windows Engineering Conference, he called it the Holy Grail of computer science. Now, to be quite honest, I don't know whether he was referring to model checking in particular or to verification in general. So what makes software model checking different? Well, let's see. I think I can see it up there better. There are large, unbounded base types, ints, floats, strings. Let's see. User-defined types, classes, pointers with aliasing, and unbounded numbers of heap allocated cells. That's a hard one. And let's see. Procedure calls, recursion, calls through pointers, dynamic method lookup, overloading, concurrency with unbounded numbers of threads. Let's see. Templates, generics, include files, interrupts, exceptions, callbacks, use of secondary storage, files, databases, absent source code for library system calls and mobile code, and esoteric features like continuations and self-modifying code, and finally, sheer size. Microsoft Word, the last time I checked, was 1.4 million lines of code. So how do you handle systems that are that big? Now, another question is, what does it mean to model check software? One approach is to use static analysis to extract a model from an abstraction of the program, and then check the model on the abstraction. Another approach is to simulate the program on all paths in the computation tree. And there's some model checkers that use this approach as well. Others look for patterns, or use a finite state machine to look for patterns in the control flow graph. And the last one is that it is possible to design with finite state software models. And you're probably familiar with some of those. State charts, for example, are an instance of a way of designing with finite state models. Now, another approach, I think this is the last one, what does it mean to model check software? Well, Daniel Kroning uses bounded model checking and SAT for software model checking. And he has a way of unwinding the program and using a SAT solver. Now, meanwhile, back at Microsoft, they developed their own model checker to verify device driver code. They found out that a lot of errors in Windows were caused by bugs in third-party device drivers that had been written by other people. And when they built a model checker that was specifically targeted to verify device drivers, and it worked. Their strategy worked. They were able to by limiting by restricting the problem to device drivers, they were able to go much further than by looking at models in general. And the people at Microsoft who pioneered this work were Tom Ball and Sriram Rajamani. And I think they're still working on this kind of thing. Now, this brings me really to the end of my talk. What's left? Well, this is what I would like to be able to check. It's definitely a circuit, and it looks like a schematic diagram that you might see an engineer electrical engineer try to verify. But if you look down at the corner here, this is the this is the P53 MDM2 DNA repair and regulatory network. What happens? Apparently, what happens at the cellular level is that if the DNA in a cell becomes corrupted, then this circuit will try to repair it, and if it's unable to repair it, then it will cause the cell to commit suicide, and that would be better than causing cancer, which would be might be one of the alternatives if the cell contained bad DNA. So this brings me to the end of my talk. I'm willing to answer questions, although I don't know if that's appropriate now. Okay. So that's it.
Ακολουθεί μουσικό πρόγραμμα από το σύνολο χορδών Κάσους Τσέλη.
violoncelli, and we're going to play some classical music and a bit of Greek music, especially arranged to honor Mr. Clarke for today's ceremony. Thank you very much. this is a song from Crete. The next one.
παρουσίασαν.